So just a little bit of history. Back in 2017, the RSGB were looking for some suggestions for the YOTA Summer Camp Buildathon in August 2017, which was hosted by the RSGB, and ended up building the QCX, which is the one in the middle. At the time, it didn't have an enclosure. That was the later addition. And that led to the QCX Plus and the QCX Mini on the left there. Those are single-band analog monoband CW transceivers for QRP, so 5 watts output. And then in 2021, I did a very high-performance embedded SDR digital transceiver, which was called QDX. Very small, it's about the size of a pack of cards. I won't say pack of cigarettes, but something like that. And it covered 5 or 6 bands with diode switching between them. So very economic, very efficient, very high performance. And then later in 2023, I married them together and made QMX. The M was for marriage, and marvelous and magnificent and all kinds of different things. And the idea originally was that it would cover just CW and digital. And later the SSB was added to that concept. Initially there were versions that covered 5 bands from 80 meters to 20 meters, but now we have also 60 to 15 and 20 to 10 meter versions. This is a nice picture of that. So 3 to 5 watts of QRP, and includes all of the features that happened in QCX, like the dual VFOs, full break-in, S-meter, but it's also got S-meter, power meter, SWR meter, all kind of built-in test tools. It also is very good with the computer because it's got built-in USB, 24-bit USB sound card, and 3 USB virtual COM serial ports for CAT control. So you can do very easily digital modes with WSJTX or other digital software, very easy to configure. That's a picture of the inside of QMX, and you can see it's pretty complex, compact I mean, and it can be done carefully. I don't think you quite need to have a Swiss watch fetish to get there, but you need to be careful. But then in 2024, I made a larger version, which was QMX Plus, which is essentially the same schematic, but it has twice as many filters, switch filters. So it covers all the way from 160 meters to 6 meters, and runs the same firmware as QMX, so all the same features. But it also has an optional GPS module you can add inside the enclosure, and a battery for real-time clock backup, as well as lots of space for expansion that you can add your own modules. And people have done modules for a charger, ATU, and speaker, for example, that slots in on top and have it all in the same box. I don't yet have an option for that, that I have an official option for that, but I would like to have one. This is a quick picture of the inside, and this was actually the revision 1 board, so the current board has a lot less that you have to do. So for example, it doesn't have these switch mode power supply boards, they're integral on the board, and the through-hole capacitors are now SMD as well, so it has less to do on the current version. There are really nice CW filters, selectable filter bandwidths from 50 to 500 hertz bandwidth, very clean sounding filters. Low latency and good break-in performance was always important to me. I'm CW operator, not an SSB operator. Not particularly good at CW either, but better than I am at SSB. I've never had an SSB QSO, except with myself when I was developing the polar modulation SSB. And it has very clean envelope shaping, Blackman-Harris shaping. So I did this comparison that you see here at the bottom right from QST reviews of the spectrum of the keying. And QMX is extremely clean there in the middle compared to some of the other transceivers. Even looks very good compared to the Elecraft transceivers. Also has built-in iambic keyer memories CW decoder. As I mentioned, the digital side of QMX has the built-in USB sound card and virtual COM serial all over the single USB cable, so it's very easy to interface. It also has a special method of counting the audio frequency and then transmitting that as a clean synthesized wave rather than SSB modulated FSK. So it produces a very clean signal. Anyway, that's the background of the whole thing. Now onto the SSB side of things. And this SSB was a kind of promise from the beginning of QMX 2 years ago. And everyone took it as a firm promise and was continually asking me when will I be able to deliver it. And there was this built-in microphone that you can see there in the middle, of the small microphone on the board, and you could also plug in a microphone and PTT. And the plan was to use envelope elimination and restoration methods to generate SSB, which is another word for polar modulation method. I actually first came across this in 2019 at the Dayton Hamvention. We had in those days ClearSpan tent, and I was a latecomer compared to all the major producers. So I was in the ClearSpan tent with the QRP Labs booth, and Tony had his own desk about 3 along from me, and so this was a picture of his 500 watt transceiver that he demonstrated his prototype at Dayton in 2019. I didn't hear any more since that in the last 6 years until this year, when suddenly Flex announced their 500 watt transceiver, the Aurora, which was basically developed by Tony K1KP from his prototype. So that was very nice to see that he did find development opportunity for that. So here's a couple of pictures from 2025. On the left, that's me talking with Tony, and we discussed for about half an hour very nice details of polar modulation. And then the Flex founder, Gerald Youngblood, there on the bottom right, and 2 of his engineers. It was a great honor for me to demonstrate QMX to these guys from the big American company Flex Radio. The next thing that was important was microSDX, which was designed by Guido PE1NNZ, originally on a QCX. So he took my QCX monoband CW transceiver and he made his own special firmware version, which made it behave as an SSB transceiver with polar modulation as an SDR. Numerous others were involved, so Manuel DL2Man, he did a lot of work on Class E filters and the output stage. Barb WB2 CBA was involved. Later there were a lot of Chinese versions of it as well, which was a bit controversial, as always Chinese versions of everything can get, and people start arguing about whether they're legitimate or not. So that gave me the idea, basically microSDX gave me the idea that rather than QMX just being CW and digital, the pure marriage of the QCX and the QDX, the CW and digital, I could also add SSB because I had the envelope shaping in there, so I could use that envelope shaping to produce amplitude modulation, and I should theoretically be able to produce polar modulation SSB just like Guido had done. And so it was kind of a huge act of faith because I had already sold about 10,000 QMXs before actually releasing the firmware for QMX SSB, and there would have been some unhappy people had I not succeeded. And so I had hoped to be able to do that, but the fundamental thing was I was using a much more powerful CPU. QMX has a 168 megahertz 32-bit ARM Cortex M4 processor with DSP and floating point instructions, huge amounts of memory and all these peripherals, so it's a lot more capable processor. The microSDX just used the Atmega 328, which was a very sort of minimalist implementation. But it really all goes back originally to 1952, where Kahn proposed in this IE paper to split SSB into amplitude and phase components and modulate these two components of the SSB signal separately, and it magically results in SSB, so the unwanted sideband and the carrier disappear. The big advantage is you don't need a linear power amplifier. This is an advantage both in terms of efficiency, but also in terms of performance, because I'll come on to this more later. A linear power amplifier is trying to get these curves in the data sheets of transistors and make them into straight lines, and that's always a losing battle. You're fighting against what the transistors want to be. And so the big advantage here was you can use a switching amplifier for the RFPA, and that results in very high efficiency and simplifies the design of the PA for a given level of performance. So here's a diagram, don't worry if you can't read it very much, from the 1952 paper, which is basically explaining on one slide how polar modulation SSB occurs. So you start off with audio from the microphone, and you do a 90-degree phase shift on all that audio, which is a Hilbert transform in DSP terms, and that gives you the real and imaginary components, which we call I and Q. The phase angle between those is just the arctangent of Q divided by I, and the amplitude is the square root of Q squared plus I squared. And then once you've got those two components, the angle and the amplitude and the angle, you can then apply them separately. The other way I like to explain this, if you think of our typical way of looking at coordinates where we have north, south, east and west, and you want to specify how far is it to London. You might say, okay, travel 50 miles east and then travel 50 miles south if you're a bird and you could fly and you weren't stopped by roads and buildings. 50 miles south, 50 miles east. Or you might say, okay, travel 70 miles in a straight line at an angle of 120 degrees, and it would take you to the same point. So coordinates can be expressed in multiple different ways. You can have a simple XY coordinate on a piece of graph paper, or you can represent the same point in space in polar coordinates as a distance and an angle. I'm sure some of you have big towers and rotators on the top, and you're used to having beam headings that you steer your antenna rotator to point at the DX station you want to talk to. Same concept. It'll be 5,000 miles that way on a heading of 180 degrees or something. So we can represent any point in space when we're looking at a 2D surface as either X and Y coordinates or as an angle and a distance. And the same really applies to voltage signals in a transceiver. We can represent them as an amplitude, or we can also represent them an amplitude that varies in time, or we can also represent them as an angle and an amplitude. So this is my attempt to explain how polar modulation occurs. In QMX, the amplitude modulation was, this is the CW shaping circuit that was added there. It's basically an amplifier with a power transistor and it just scales up the digital to analog converter output of the CPU to a supply voltage for the power amplifier. And the big advantage of doing your amplitude modulation at audio is that you don't have to deal with a lot of effects that you have to deal with at RF. So you can have multiple transistors and you can have feedback mechanisms, as you see here in this feedback mechanism here, which provide a much higher linearity. It's much easier to get linearity at audio than it is to get it from an RF power transistor. Then on to the phase modulation. We generate the actual signal in QMX and in QDX, even in QCX, with a marvelous PLL synthesizer chip called the SI5351, or its Chinese version MS5351M. And you can ask for any frequency out from this thing and it will give it to you. It's on an I2C bus on the processor, and you can update that at up to 16,000 samples per second. Now, the very important thing to realize is when you're applying, what you apply to the synthesizer chip is a frequency change, not a phase change. So you have to think about how to get a phase change indirectly. And the way I like to see this, if you look at this diagram on the bottom right here, if you had two signals, which I've indicated here with the red and the black sine wave, if they're offset by 1 hertz, so for example, one of them has 10 million cycles per second, and one has 10 million and 1 cycles per second, if you start them both at the exact same point, at 0, so they're in phase at time 0, by the time 1 second has passed, they'll come back into line and they'll be at exactly the same voltage again. They'll both be at 0 again after 1 second. But 10 million of one of them will have passed, and 10 million one of the other one will have passed. And so the important thing is, if you decided you want, so you've got then a 0 phase shift after 1 second, or a 360 degrees if you like. If you wanted to have a 180 degree phase shift, you could stop the situation at half a second. If you wanted a 90 degree phase shift, you could stop the situation at quarter of a second. Or if you wanted a 180 degree phase shift in quarter of a second, you could have a 2 hertz frequency separation and just run it for a shorter time. So you can play around, and what you end up with is applying a series of frequency changes which are calculated that at the end of each sample they've produced the desired phase shift, just by how the signals drift relative to each other. So this was the very powerful concept which Guido PE1NNZ developed for the micro SDX, and which we also use in QMX. Now a little bit about how we test SSB and how we judge the quality of an SSB modulator. There are always two tones, and conventionally we use 700 Hertz and 1900 Hertz. They have to be non-harmonically related. And we put those two tones together into an SSB transmitter and look at the output on the spectrum analyzer or an oscilloscope. If you put it on an oscilloscope, you see something like on the left there. But you can't really make any decent measurements from that of how good or bad the transceiver is. It will look like that even if it's fairly bad. It will still look okay on the oscilloscope. So the real thing you need is a spectrum analyzer, and you see these two peaks in the middle which correspond to the 700 and 1900 Hertz tones coming through. But then you also see this forest of nonsense on either side, which are the intermodulation products which occur because of non-linearities in the SSB amplifier. These you don't want. All these side products you don't want. And if you look at one number which expresses the decency of a SSB transmitter, it's the third order intermodulation product, which is the first of these spikes as you come down from the two wanted signals in the middle. So you look at the height of that spike relative to the height of the wanted spike, and that's the IMD3 in dBc, dB relative to carrier. The ARRL have a slightly different method of specifying it in their QST reviews, which involves dB PEP, which is just 6 dB more than dBc. So you have to be careful that you're comparing like with like. There was a web page by VK2IHL where he gave his opinion, which I gathered was fairly consistent with what was generally consensus. And minus 40 dB he said would be really excellent, minus 30 dBc was good, 20 was poor, 10 was very poor, and minus 5 was what he measured on the micro SDX. So again, this is not a criticism of the micro SDX. It tried to achieve a lot with a very rudimentary amount of hardware and CPU processing. So now on to how I actually made this work, and I'm not going to talk about pain or torture. You heard me talk about that last night. But to start off with, well, I'll talk a little bit about pain and torture. To start off with, just feeding in one single tone into the system results in a nice spike like that. So it's a good start, and it was nice to see that basically something is working in the system. The amplitude modulation was also working very nicely. I was able to provide a signal to the digital to analog converter and see that reflected in the RF envelope, which is the blue trace at the top on the oscilloscope. So that was good. When I applied an audio signal to this amplitude modulation, I also got something that was okay. That's how AM is supposed to look on a spectrum analyzer. These two little spikes down here are not what you want, but they were quite a long way down, so that is again a great start. But when it comes to SSB, I just couldn't make this work at all. And this was where I spent my 3 or 4 weeks headbanging and despair. And so these were some of the scope photos I took during those horrible 4 weeks where I started to doubt whether I would actually manage this or not, and started preparing all the apologies I was going to make to people who had bought QMX with this promise that it was going to have SSB. So I couldn't make these nice two peaks appear no matter what I tried. And I started to think that maybe Guido was making everything up. Khan had been making everything up. Even Tony K1KP had been making everything up. And I started losing optimism completely and working in the middle of the night, and it was, it was a very difficult time. And you know, if you're a kid and you made one of these one transistor FM bugs, and you could just about decode it if you were in the other room next door, and it wasn't really very good FM. Even if you'd had an AM receiver in the room next door, you would also be able to decode it. And I kind of thought maybe it's like that, you know. But then I had the idea to compile in Guido's code, and it was actually, I was talking with my friend Ross, EX0AA, on the phone, and we kind of were discussing the problems I was having, and we both came to this same conclusion. I could just take Guido's open source Arduino project and paste it directly. And he was using 16-bit integers, I was using floating point. He was running at a much slower update rate of only 4.8 kilosamples per second. He had approximations for everything because he didn't have time in his CPU to calculate arctangents, square roots, and Hilbert transforms to a high accuracy. So, but I was able to convert my floating points from the microphone system into integer and then on from there into Guido's code. And magically I saw these two peaks. When I fed in a 600 Hertz and an 850 Hertz signal, I got the two peaks come out. I wasn't terribly impressed by all the rest of the stuff, but at that point, I finally saw two peaks, and it was a great moment. And this is, you know, my favorite photograph from the whole project for that reason. But of course I was hoping to improve on that, because all of this other stuff around the side would not sound particularly good on nearby frequencies. So as I went through line by line, changing one line of code to the next until I found the problem, and my friend Jamal, TA2BG, who's a university physics professor at Ankara, he came over. He has a holiday house nearby to where I live, and we discussed this for literally 8 hours solid. Every now and again my wife would call me on the phone, "Where are you? What are you doing?" Still talking to Jamal, you know. And we figured out everything, that because I had used the arctangent function, and tangents repeat every 180 degrees. They have this kind of shape like this, every 180 degrees, whereas sine waves repeat every 360 degrees. So when you come to do the arctangent, which converts back from the tangent to the angle, you get a result in the range plus 90 to minus 90. So I was losing half of my polar modulation. It's like if you imagine on a latitude, longitude description of coordinates on the Earth, if you said, okay, my longitude is 45 degrees, but you didn't say whether you meant 45 degrees east or 45 degrees west, you've lost half the hemisphere, you've lost half the information. And so that was the problem, that was all it came down to. So Jamal told me in the math.h C library there's another function, atan2, where you pass in the two parameters and it divides them, and it takes into account the quadrant and returns a function in the an angle in the range minus 180 to plus 180. So it was a great moment. Then I started working on all the other problems I had, and I had this distortion in the modulator where it had several issues. The first one was the overshoot. So you got these kind of spikes here. When you made a big step change in the amplitude, it would overshoot and then come back. Correspondingly, on the way down the amplitude on the other side, you got this kind of slow decay. And then it didn't go quite to zero in the middle either, which was another problem. So I started trying to solve all of these problems, and again, they were huge weeks of work. And I solved the overshoot by amplitude interpolation. So I ended up with 28 linearly interpolated points between each of the original points, and it produces a much nicer, you can still, if you zoom in, you can still see these overshoots, but now you've got 28 little steps on the staircase with little overshoots, rather than one big overshoot on a big step. So that was a big improvement. And then at the zero crossing, I was able to switch off the signal completely when it was below about 1 volt peak to peak, and that improved that situation. A key fundamental requirement of the whole project was that I couldn't change the hardware. So if I had discovered that something was a fundamental blocking for the whole situation, the whole SSB project, I couldn't go back to the 10,000 people and say, can you start soldering SMD components and making modifications? So that was, luckily I had no showstoppers, but I had all these little wrinkles that I had to work around. The next thing I looked at was phase pre-distortion. So when you have a signal passing through your power amplifier, even if the amplifier is in class D as in QMX, you end up with a variable phase delay which depends on the amplitude of the signal. And I was able to correct for that by measuring it using an oscilloscope. So I fed in one oscilloscope channel the signal at the beginning of the PA and the other one at the end of the PA, and I was able to then freeze the oscilloscope and measure the phase change. And that was something that I really didn't want to have to measure by hand and code into the system. The Polar Explorer article in QEX 2017 had a shape very similar to mine. So mine is there on the bottom left, and they had seen something that you see there on the right. That's taken from the QEX article. And Polar Explorer used the AD8302, which even in quantity was a $19 chip. Whether or not they still have that in the Aurora, I don't know, because Mike, I'm trying to push him for details of this, but he won't give me any details of the schematic. We can ask him, Mike, all these people all these people might put pressure on you. So they had this very expensive chip to measure phase and amplitude distortions and to correct for it. But I was able to come up with a way of measuring the QMX to measure itself. So there's a transmit-receive switch, which is shown here on the right-hand side, and it kind of mutes the receiver during transmission, but it only has about 30 or 40 dB of attenuation because it's just a simple transistor. It's not really a mute, it's just to save the receiver downstream from a huge signal which would fry all the components during transmit. And the interesting thing is that if you operate the receiver and the transmitter at exactly the same time, and you start both the transmitter signals and the receiver signals in phase at the same time, and then you suddenly offset the receiver oscillator by 5 Hertz, you can then count the zero crossings, and you can see how long it takes you to count, say, 5 cycles. And you also know how long it should take to have 5 cycles, because you know at exactly what point you change the frequency by 5 Hertz. And the difference between what you measure and what you thought you were going to get is the phase delay through the system. I couldn't believe that that would possibly work. I'm sure none of you can believe that either, or most of you can't believe. But it actually did work, and I was able to obtain very close to what I measured on the analog measurement by hand. So I had to do all these tricks, like because the signal was so huge, in some cases I had to run the receiver at 1/3 the transmission frequency, so that I would be receiving the third harmonic to reduce the amplitude. And in some cases using different bandpass filters to the correct one for the band, so that it would just reduce the amplitude. But this was an example left and right by my manual method, which I did on the 40-meter band, and by the method that was measured using the self-measurement internally in the software. So I was very, very happy with that. I was also very happy because you could do that at 40 meters, but by the time you come up to 10 meters or 6 meters, unless you have a gigahertz oscilloscope, things starting to look very difficult to make any decent measurements at those high frequencies. But with this method, you can do it. Then the next question was about amplitude and phase synchronization, the modulation. Because when you do the frequency command to update the frequency for a new phase, that phase only comes to fruition at the end of the sample. By that time the phase has slid to where you expect it to be. And there are all kinds of delays, like how long it takes to send this serial data over the I2C bus to the PLL chip. All sorts of delays everywhere, which is very hard to calculate for or predict. So my next question was I going to be able to have an automated method to determine this optimum synchronization? Now on the left you see a poorly synchronized phase and amplitude modulation. On the right you see a well-synchronized one. And you can see that the well-synchronized one has very much lower intermodulation distortion products compared to the one on the left. I was actually able to do this by transmitting a two-tone test into the transmitter to produce this spectrum analyzer plot, but then running the receiver at a 2.7 kilohertz offset through the transmit-receive switch, which was switched off, and then summing up the content of what came through in the receiver. So when the receiver was off by 2.7 kilohertz, it's receiving the section of band in this white box, which contains the 3rd, 5th, and 7th intermodulation products. So I was able to sum those up and obtain some kind of relative measure, at least, of the intermodulation performance of the transceiver. And so with that, I was able to vary the synchronization between phase and amplitude in steps of 1/28th of a sample, and plot internally plot the amount of 3rd, 5th, and 7th harmonic, and find out exactly where the minimum was, and use that then as the synchronization delay between the two. So these self-calibration tools provide maybe 10 dB of improvement in intermodulation performance when you run them. And of course they're measuring your own particular radio, which may have different component tolerances to someone else's. So in my final implementation, I had to balance everything up, and even 168 megahertz CPU, you quickly run out of time. And I had, in the end, my transmit logic was using 93% of the CPU. And I had run the DSP at 12,000 samples per second with 28 points interpolation on the amplitude, and using the direct memory access to peripheral in the processor to stream these samples very accurately. And it results in about a minus 35 dB for the IMD3 product. By comparison with other transceivers, the Elecraft KX2 and K3S have approximately the same IMD3 number. So I was quite pleased with this result, considering I originally expected to do better than the micro SDX had done, but I didn't expect it would be that much better. So a couple of other things I'll just try and skip through quickly because I think we're running out of time, and polar modulation was the main point. Controlled envelope single sideband is another thing which I implemented in QMX. Basically, when you SSB modulate anything, you get an amplitude overshoot of the amplitude RF envelope, and a conventional transceiver will then reduce the gain, probably automatically using ALC, in order to prevent that RF clipping, which would cause SSB splatter into adjacent channels. So controlled envelope single sideband is a method for controlling those overshoots and removing them without causing distortion. So that was a picture of a typical SSB. So you start off with perfect audio, perfectly bounded ±1 notional amplitude, but when it comes through on the output, you can see my blue dotted line here. That's the full amplitude, so you get these considerable overshoots, which would cause horrible splatter in practice. On the left side is without controlled envelope, on the right hand is with controlled envelope, and you can see the big difference there. And what it typically means is that a 5-watt CE-SSB transmission has about the average power of a 12-watt normal sideband transceiver, because it increases the average power without the distortion. You can choose the audio source for QMX SSB audio from the internal two-tone generator, or from the microphone, or from USB sound card if you want to do digital modes. There's also parametric equalization, so DXs say you should boost the treble part of the audio and reduce the bass part of the audio, and you can set all of that up exactly how you want it. You can see on QMX, you can see this on the LCD screen with a miniature kind of graph that you see there on the bottom left. Or if you have a terminal emulator and log into it with a terminal emulator on a PC, you can plot the graph shown there on the screenshot. So just in summary, the CSSB feature the transmit equalization. We also have compression, so you can control the amount of compression between 0 dB and 99 dB, which would of course be utterly ridiculous, but anywhere between 0 and 15 or something you can experiment with varying levels of distortion. There's microphone gain and AGC, voice-operated transmission, noise cancellation, noise gate, phase pre-distortion, and all of these self-calibration tools. So why I love polar modulation? Well, I'm so excited about polar modulation. I may not look very excited, but that's because I'm English. So I'm understated. But it gives a very surprising level of performance. I got -35 dBc. By comparison, I had previously designed a 10-watt linear when I was working on the QSX project, which has now been cancelled because QMX Plus does everything that QSX was going to do. And this performance level is about 10 dB higher than we had in that. Of course, IMD3 is only one measure, it's not the only thing, so there's still a lot of potential for further improvement as well. But the most important thing, I think, is that you have these curved characteristics in the data sheets, and for the last 75 years or whatever people have been using transistors in power amplifiers, engineers have been fighting to make those curves into straight lines. And it's putting a square pole into a round hole. It doesn't really want to happen. It's unnatural. And so it's an abomination really to do that. So a linear amplifier is really not the way. And so with this method, polar modulation, your amplifiers are operating in class D, which means that transistors are completely on or off, and you don't care about the curves anymore. You don't need to buy any expensive transistor which has had its curves nicely tweaked to try and be good for SSB. You don't need any of that. It just needs to be on or off. Guido, I have to mention again because we stand on his shoulders. I know that Flex were developing from Tony K1KP as well. And but Guido really showed how you could do it on very simple hardware. So the long battle was really worth it, and I want to emphasize again 3 huge advantages. The higher efficiency is one of them because you can use switching amplifiers, class D, class E amplifiers. You don't have to use a linear amplifier. That results in lower cost, cheaper transistors, smaller heat sinks, smaller power supply, smaller enclosure, and for any given level of skill and expertise, which mine is not very high, we have a higher level of performance. So you can imagine if it takes 20 RF engineers to make a good linear amplifier, it takes one clown like me to come along and you can just about manage to make a polar modulation SSB. And so I think it's a real game changer for the industry, because it's not just very high efficiency, but the lower cost and the shortened development time to achieve a given goal. And you can see this in Aurora's Flex's Aurora, which they have along by the Martin Lynch stand. The heatsink for their 500 watt transceiver is the same size as the one they use in a 100 watt transceiver. And the enclosure is the same size, but they've also included the power supply. And so it's an amazing, amazing technology. This is just a quick summary about this is the shameless commerce division plug, where I show the QMX and the prices of the QMX. We sell them both as either a kit or as an assembled transceiver. And finally, we have our forum, we have our webpage, my email, and YouTube channel. And so I managed to get through all of that in a reasonable time.
Brilliant.
Thank you.
Any questions?
Thank you.
So does anyone have any questions? You were first hand up over here.
Hello,
can I just run away at this point?
It's Mike, G4CDF. Thanks, you gave us a talk at Reading and District Amateur Radio Club not long ago about this. I have a particular question. Is it possible to add a homebrew amplifier onto the end of your transceiver?
It is.
And gain the advantage of the polar modulation? And how would you do it?
Well, you mean to get a higher level of power output?
Yeah, say to make a 100 watt amplifier, but with using the Class D modulation. Is it possible to interface such a beastie into the QMX Plus?
That's a very interesting question.
I knew it is. I knew it was.
I think that should be possible to do, and it's not something I've yet tried, but I think that should be a possibility to do. The other thing people sometimes ask me is for controlled envelope sideband. Do you still get the controlled envelope sideband if you run it through a conventional linear afterwards? Right. And the answer is yes, you do, because once you've got rid of those overshoots, they're gone forever. Right. And the linear is just amplifying what goes in and what comes out. But the question of going to higher power and how you do that, and whether you do it as an add-on amplifier or as a new device is an interesting one.
I think it'd be really cool if you could take your rig and amplify it up. Yeah. Even if you needed some feedback or
to measure the
special
phase
amplitude modulation output or whatever. Thank you.
Any promises?
No promises. I'm never going to promise anything ever again. So.
We've spent the last few decades getting our transceivers better and better on phase noise and getting them ultimately to decay away. And it's ultimate attenuation, which is very important. The third order is pretty much in your own channel. What target do you think you need to achieve with this method 20 channels out?
I don't have a number in mind, but I agree with you, it is a challenge. And you find with a conventional linear that the higher order intermodulation products decay quite quickly.
Depending where the bias is set.
Right, whereas with
low bias, they'll be very high. High bias, they drop away.
Which also makes it very inefficient, right? Whereas with polar modulation, these higher order products tend to decay much more slowly.
That's the problem.
And that is the problem. And so the solution, there are solutions to that, which is you can, there's a rule of thumb which says that your processing speed, your DSP sample rate, should be 5 times the maximum audio bandwidth that you want to cover for a 30 dBc IMD3 performance, but it also affects the higher order products. So the solution is to get faster, but that involves faster CPU, more current consumption, and as every time you go faster by a factor of 2, your CPU cycles increase by a factor of 4. So a lot of unpleasant things happen.
So it would be if that transmitter was a neighbour of mine.
Right. But I believe,
so
for
I think,
example,
you've been using the third order value of, 30,
it's a single
40
number
or
only.
minus 5. There needs to be a stake put in the ground by users of this technology for the ultimate level it will be.
Yeah.
I think it's extremely challenging.
It is extremely challenging, and it should be the aim should be to reach a comparable level that we get with a conventional sideband transceiver, I believe, a conventional good one. So it does need to be improved. Increasing the processing speed, I mean, I believe Flex do it at 96,000 kilosamples per second, which is a much higher rate than I'm capable of in my CPU. But they have FPGAs and all kind of stuff going on in there. So yeah, that's a very important consideration, and it needs more work, I agree.
Marek, M0JUR. So first of all, I'd like to thank you, because I've been watching QRP Labs rigs for quite a few years, but not being a CW operator, yes, I know, I'm really going to get to it someday, probably like when I retire or something. But yeah, I've really been looking at kind of the lack of SSB has been was a bit of a blocker for me, and now, well, I actually bought the QMX Plus in the summer. You might recall we had some problems with the wire delivery, but so I don't actually have to thank you or curse you, because now I have got no excuse but actually start taking that thing with me to SOTA, because before too big. But I really love the idea, the fact actually, of course, that's largely Guido's work, but the fact that this really shows what we can still achieve as improvements in amateur radio. Of course, I suspect there are probably some clandestine sets out there which GCHQ and the like use, which already use this technology for years, but this is something new. But yeah, question. What do you think you're going to do now? Are you got so fed up with this fight with the SSB that you're just going to hide for a year? And
I said, just now, I said no promises. Secrets only. The problem I made earlier with in 2018 when I did the QSX transceiver for Yota in 2018 in South Africa, the problem there was the pressure afterwards when everybody knew what I was working on. And everybody wanted to know when will it be finished, what features will you put in, and it ends up mentally destroying you. And so I decided after that, everything I do will be by surprise. So I declined to answer your question.
Any more questions or comments before we wrap things up? Are you taking orders now?
For QMX and
Yeah.
QMX Plus, we are, yes.
No, it's taking orders now.
So we've sold almost 13,000 of these two models, QMX and QMX Plus. We sell them as kits and as assembled radios, and so they're very popular.
Okay. Well, if you want to order one now, can you go to another corner of the room, because we have another lecture coming up. Would you give you a round of applause to Hans? And thank you. Remarkable.
Thank you.
Remarkable. Thank you very much.